Hi everyone, my name is Cheng. I'm the MI physicist at the Imaging Research Facility of Indiana University. Today, I'm glad to have this opportunity to talk about tissue classification of the brain using diffusion MRI signal. So why do we care about brain tissue classification or segmentation? First of all, there are clinical applications such as delineating lesions or surgical planning. The brain segmentation is also critical for volumetric analysis. In functional MRI, brain segmentation can help with brain registration and removing spurious activation. In diffusion MRI, segmentation can also help brain registration, and in addition, it's very useful to guide fiber tracking. For most applications, segmentation is performed on T1 weighted image. Because the T1 weighted image has high resolution and low geometric distortion. However, there is confound for T1 weighted image for segmentation. It may suffer from B1 field inhomogeneity and may provide non-optimal contrast. For instance, in this case, in the neonatal brain, the contrast between gray matter and white matter is not decent. Also, the segmentation needs to be warped to fMRI or dMRI image space, which may introduce some errors because fMRI and dMRI images are typically acquired with echoplanar imaging that is prone to susceptibility artifacts. The Dipy offers a simple tool to perform segmentation on T1 weighted image. The algorithm is based on hidden Markov Random Field theory, similar to FAST of FSL and HPRS of ANTS. So you just run this simple command, then it will output nice images of CSF, gray matter, and white matter, the probability map of these three classes. As I mentioned earlier, segmentation on T1 weighted image is not perfect. So for dMRI application, segmentation based on dMRI images has several advantages. First, it can provide complementary information arising from the microstructure. Again, this is an example of the neonatal image, the DTI, and show very good contrast between the white matter and gray matter than the T1 and T2 weighted images. It also helps with spatial normalization of diffusion tensor images. And tissue classification helps tractography. There's no need to do correlation between with diffusion image and T1 weighted image. Moreover, it is less susceptible to signal inhomogeneity. Roughly speaking, there are mainly two approaches for segmentation on dMRI images. Either by generating images from DWI with tissue contrasts or using the DWI images or signals directly. There are many ways to generate images with tissue contrast from dMRI data. I will go through 4 of them. The diffusion matrix from DTI or DKI, and spherical mean, and an isotropic power map, and a power law between direction average signals and p-value. Okay, so back in 2003, Liu et al. First applied 7-channel fusion on parameters derived from diffusion tensor and showed reasonable good segmentation results. So they used ADC and the eigenvectors of the diffusion tensor and along with FA, RA, and VR. Together, the 7-channel fusion gives much better results than those using these parametric maps alone. And recently, Cheng et al. They developed a deep learning method based on segmentation, based on by computing DKI-based image features and learn segmentation from tissue labels derived from T2-weighted image. And the result is very good. So they derived a bunch of DKI metrics like MK, AK, RK, and along with FA and the eigenvectors. And then they learn from the tissue classification from the T2-weighted image. Then they apply this model to the new data, and they originally this model was computed on the HCB dataset. The learning was on the HCB dataset, but they applied to even clinical dataset. The result is very good. And by using spherical mean technique, Caden et al. Showed that the transverse and the longitudinal diffusion coefficient can very well separate the brain tissues into gray matter, white matter, white matter, CSF, and partial volume effects. It is worth mentioning that the anisotropic power map derived from spherical harmonic expansion of DW signal also resembles the T1-weighted image. So you can compute an anisotropic power map from using this equation, and then you can see that this anisotropic power map resembles the T1-weighted image. They look very similar. Next, I will introduce a new method we developed recently. It is very simple but robust. It is based on the observation of distinct response to B values for different tissues. So yeah, I borrowed this map, this figure from the paper by Garrison. And you can see that the CSF, gray matter, white matter, they have distinct response to the diffusion gradient at different B values. A simple power law relationship is found between direction average signal and B values by McKinnon. So they did the up to B value of 6,000. They observed this linear relationship between the log of the signal, direction average signal, and the log of the B value. And the coefficient alpha and beta varies with tissue types. So for white matter, alpha is close to 0.56, and for gray matter, alpha is near 0.88. So this nice feature can help us to separate white matter, gray matter, and CSF. Let's take a look at the alpha and beta maps for 3 HCB subjects. So we can see apparently alpha map is good to separate gray matter and white matter, but not CSF, because CSF here, they look pretty much like gray matter. But we can take advantage of beta, and beta can sort out CSF nicely. There's not much contrast between gray matter and white matter. So hence, we propose to use direction average signal of DW images to classify brain tissues into CSF, gray matter, and white matter. First, we exploit the beta map to find the CSF mask, and then the mask of the gray matter and white matter. On the other hand, we invert the contrast of alpha map and to get this, and multiply by the gray matter and white matter mask to form a pseudo T1 weighted image. Then we can apply standard segmentation algorithm to the pseudo T1 weighted image. This figure shows that the pseudo T1 weighted image is very similar to the T1 weighted image. Okay, here's a comparison of the segmentation results from SPM12 using the T1 weighted image and pseudo T1 weighted or composite image and the true T1 weighted image. The segmentation from the composite image is in black and white and overlaid by the segmentation using T1 weighted image, which is pink. And the threshold of the probabilistic map is set to 0.5. And you can see that the overlap is between these two segmentations is very well. There's a very large overlap. The discrepancy is pretty small, like the pure white or red color. And this method is robust against downsampling. We compared the DICE score between segmentation results of the proposed method and SPM12 on 3 HCP subjects using A, the full data set, B, 2 shell data, the B value of 1,000, 2,000, and C, only 1/3 of the data, but still 3 shells. And we also compared the DICE score between SPM12 and FSL here. So the results show that there's not much difference by downsampling the data. The DICE score is still around 0.9 for both gray matter and white matter, which is comparable to the DICE score between FSL and SPM12. This table shows the mean and standard deviation of the DICE scores between segmentation results of the proposed method and SPM12 on 10 HCP subjects using A, the full data set, and B, 2 shell data, and C, 1/3 of the data, but 3 shells. So the mean DICE score is 0.908 for white, around 0.9 for white matter and 0.89 for gray matter and 0.78 for CSF. They're pretty good. And the effect of resolution is also explored. DICE score between segmentation results of the proposed method on low resolution DW data, which is 2.5 millimeter isotropic, compared to the 1.25 millimeter isotropic data showed previously, and SPM12 on high resolution T1 weighted image resampled to the same resolution for 3 HCP subjects. Overall there is a slight small decrease of the DICE score from high resolution to resolution, but this number is very small and not always. decrease. Okay, so we can take a look at the meaning of alpha and beta values. So the beta value is, by definition, is a log of the signal normalized by B0 image. Because there's much bigger signal change from B0 to high B value for CSF than gray matter and white matter, the beta map is good to separate CSF from gray matter and white matter. Here, I'd like to remind people that mean diffusivity computed using all three shells and one shell, this three shells is one shell, may differ significantly. So just be cautious. Yeah, as a comparison, the beta image here seems better than mean diffusivity to separate CSF from gray matter and white matter. For the meaning of alpha, we hypothesize that alpha is related to the neurite density, at least in the white matter, as suggested by the high correlation between alpha and FICVF computed from Noddy model. In gray matter, it is more complicated. Further investigation is needed to find the physical meaning of alpha and what microstructure information it conveys. And this method will be implemented in Dipy, so stay tuned. Okay, let's switch the gear to second approach for brain segmentation using the DWA images or signals directly. Well, the signal response to diffusion sensitizing gradient is also distinct for gray matter, white matter, and CSF. So this figure shows DWA signals of representative voxels for CSF, gray matter, and white matter. They are quite different. Yeah, so CSF has a big job, and the white matter, this fluctuation is much larger than CSF and gray matter. So therefore, it is possible to classify the tissue solely based on the DWA signal. Here we present a recent work using sparse coding to fully segment the brain based on DWA images. The basic idea of sparse coding algorithm is to represent a signal with a sparse linear combination of atom signals. Here's the objective function. There are two important parameters, n and gamma. So n is the number of atoms, predefined atoms, predefined number of atoms, and gamma is a regularization factor that determines the sparsity. Maybe it can be better described by this schematically by this diagram. So there's a dictionary, and each item in the dictionary is called an atom. And then a signal can be represented by the sparse linear combination of the atoms. Yeah, so here's a signal is like represented by combination by the combination of three atoms in this case. The key to this method is that is the sparsity of the combination of the coefficients. For DWA dataset, so each voxel has a time series signal, which is a response to diffusion sensitizing gradients. We can imagine that there are a number of white matter atoms and gray matter atoms and CSF atoms. And the signal can be represented by these atoms in a sparse fashion. And based on the coefficient, we can assign the voxel to gray matter, white matter, and CSF accordingly. So this is a flowchart of the algorithm. We first take the logarithm of the DWA signal. Then, using sparse coding to find the dictionary, and then to classify the atoms based on their features. Then we compute the coefficient of each atom for each voxel. Then using the voting mechanism to determine which class the voxel belongs to, or the probability of belonging to a class. Then so the segmentation is realized. Here are the results of 10 discriminative atoms and coefficient maps. Out of the 10 atoms, 2 are CSF. Here, 2 are CSF, and 2 are gray matter atoms. And 6 are white matter atoms. Yeah, you can see that the white matter atoms are quite distinct from the CSF and gray matter atoms. And gray matter atoms can also be, by looking at the map, they're quite different from the CSF maps. And even the feature of the time series, yeah, you can discriminate them too. Gray matter, CSF, yeah. And here is an example of a white matter signal representation. The raw signal, and then take log, and it can be represented by linear combination of 3 white matter atoms. And so in this case, the voxel is 100% white matter. So the one tricky part of the algorithm is the selection of the 2 parameters, n and gamma. To consider different acquisition schemes, we synthesized 6 DW datasets from each HCP dataset. We basically downsampled to windshield, to one shell, 2 shells, 3 shells, and then 96 directions and 32 directions. So that 6 DW data, 6 new DW datasets, sub datasets in total. And then we vary the number of atoms from 10 to 40, and the sparse parameter gamma from 0.05 to 1. And for each data set, the dice score using different combination of size and gamma was compared against the best one. And yeah, so we compute the dice score for each combination of n and gamma. And here you see that this parameter selection result suggests that dictionary size of 15 is optimal. And gamma has a range of 0.2 to 0.6 in this range. So we have similar good results. So we used gamma equal to 0.3 and n equal to 15 in the implementation. Okay, so here's a example of the result. We obtained pretty good agreement with segmentation of structural images. The segmentation from our segmentation, black and white, is overlaid by the segmentation from SPM 12 using the T1 weighted image, which is red. The overlap of the 2 segmentations is shown pink in the figure. It is also robust against downsampling. So without downsampling and downsampling, here there's not much difference actually. And the advantage, although by looking at the dice score, they are slightly lower than those from the previous method using direction average signal. But this method has an advantage. It can work on single shell data. Yeah. And It's very interestingly, the probabilistic map shows slight difference between cerebellum and the cerebrum. Yeah, I think that's because the response of the microstructure of the cerebellum and the cerebrum of the white matter of gray matter is slightly different, and so their response to the signal, to the diffusion sensitizing gradient is also different, and then you see these slightly different maps. And a comparison with other similar methods using exemplars of white matter, gray matter, and CSF shows that our method performs better. Here our dice score is higher than YAP's work. Okay, so in summary, tissue classification of brain can be realized from DWI images with high accuracy. Especially parameter maps derived from DWI offer various feature contrasts. And temporarily, tissue characteristics are also embedded in DWI time series. So these features are good for segmentation using the DWI images. Okay, I think that's all. Thank you for your attention.